Okay, so in this video we're going to go over the end behavior of our polynomial functions, and this was discussed in the previous module as well. All right, now in terms of our function, our polynomial function, right, it looks something like this. All right, so what determines end behavior is always the leading term, right? Now the rest of the polynomial, right, this kind of will essentially determine the local behavior, what happens in excuse me, the local sense, near, right, kind of in, excuse me, the origin, right? But as we get further and further out to infinity and in the other direction negative infinity, right, or x as x goes in that direction, then this term here, the leading coefficient, the leading power, the leading term, excuse me, and the leading power is what's going to determine the behavior of the graph, right? So there's four possibilities, right? So, and those possibilities are a combination of whether this is positive or negative, and whether this is even or odd, right? So let's look at the case where n is even and a sub n is positive, in other words, greater than 0. Right, so when we have something like this, the behavior of the graph looks, and again, just the end behavior, right? It looks something like this. Now, there may be some kind of interesting behavior in the local sense around here, but I'm not too concerned about that, right? Now, all I'm concerned about is the end behavior, right? So I'm concerned about two different quantities, right? I'm concerned of what happens to the value of the function as x goes to infinity and as x goes to negative infinity. Right, and as we can see from here, right, as x goes to infinity, my function f of x also goes to infinity. And the same thing here, as x goes to negative infinity, the function goes to infinity as well. Right, and that's what these arrows will represent, right? As x goes to infinity, the function values also go to infinity. As x goes to negative infinity, the function values go towards positive infinity. Okay, remember x input, f of x is the output. All right, so that's one of the cases. So let's look at the case where, let's say, n is even still, but now a sub n is negative, less than 0. So what changes here, remember that leading term being 0 reflects the graph across the x-axis, right? So what happens here is that we get this case here. Okay. All right. And again here, all right, we're looking for what happens to the function f of x for the two different quantities here. X going to infinity, x going towards negative infinity. All right, and here, as x goes towards infinity, that function goes towards negative infinity. And here, as x goes towards negative infinity, the function values also go towards negative infinity. Okay, so we get something like that. Okay, and again, whatever happens here really depends on what all these terms are, right? And we would use the techniques we've used previously, factoring, finding x and y intercepts to get a accurate representation of what happens in here. But the end behavior, right? I only need to look at that leading term and the coefficient and degree. The degree is what's going to guide me to this end behavior. All right. So the other two cases we haven't looked at when n is odd. Right, so we have two more cases here. What happens when n is odd? And it's the leading coefficient is positive, right, greater than 0. Okay. So when that happens, right? We get the behavior where, right, that positive term, leading coefficient makes it go to 0. But as x on this direction, it goes something like this, right? Think of the cubic, right? That odd power, when I put in a negative power, a negative value for inside an odd raised to an odd power, I get in return a negative number. All right, and again, we're looking for two quantities here. We're looking for quantities when x goes to infinity and x goes to negative infinity. And we can see from here, as x goes to infinity, the function also goes to infinity. All right, and then here, as x goes to negative infinity, f of x goes to negative infinity as well. All right, okay, and then here, the last case here is what happens still n is odd. But here, a sub n is negative. So again, here, these get flipped across the x-axis. Right, that's what that negative does. So what we wind up with is a odd degree polynomial, right, where the n behavior looks something like this. All right. So here, as x goes to infinity, x goes to negative infinity. We see here as x goes to infinity, look at this one first, the values go towards negative infinity. And as x goes to negative infinity, the values go up towards a positive infinity. Okay, so that is a summary here how the degree dictates, the degree and the sign of the leading coefficient dictates the n behavior, right? And again, n behavior is, we're only worried about that leading term. Okay, all right. Now, let's take a look at another property of polynomials. We also started discussing in the previous section this idea of turning points. Okay, now so we'll take a look at here something like this. And so it looks like a cubic type function, right? It crosses the x-axis 3 times. Right? And also the way it crosses looks like just kind of like a straight line, just kind of going through the axis. So that leads me to believe this is a cubic function. Now, this idea of a turning point, and I want to kind of mark off these points here, right? So almost think of like if we're going on a ride on this curve here. Right now, as I go up this way, right, here, always reading from left to right. Right, this is increasing. Then I reach some kind of peak here, right, maximum here. And I notice here it's not a maximum of the whole function, right, just kind of around here. Again, we keep using this term nearby, and again, we don't really strictly define that. When we get to calculus, we'll have a more, I guess, rigorous definition of what it means to be near, right? But the point is here that it reaches some kind of max nearby where this point is higher than any point near it. And then after that, it's no longer increasing, right? Now we're on the way down in our roller coaster ride. And now it starts to decrease. And then we decrease, and then we hit this kind of low, right? This minimum. Right? And again, this is what we call a local minimum, right? Where we think of values nearby, right? This is the lowest one. right? And here nearby here, this is the highest one, or the max value. Okay, and here we decrease, and then once we kind of hit that low, that minimum, then it bounces back up and we are back to increasing. Okay. All right, so this idea of a turning point is where we have this behavior that we change from increasing to decreasing, right? So this is one turning point. And this is another turning point. All right. And notice here there are two turning points for a polynomial that is of degree 3 here. Now the turning point and the degree are related here, right? Now we can generalize here to say here just in general a polynomial of degree n, right, and some whole number n, has at most n minus 1 turning points. Okay, all right. So again, for this one, we have a cubic, right, degree 3. So it had, at most, in this case, it had exactly 2, right, turning points. Right? This being a turning point and this one being a turning point, all right? Pay special attention to the language. At most. Doesn't mean there will be, but at most n minus 1. Right? There could be less, but not more, right? N minus 1 is the cap, right? So a polynomial of degree 5 has at most 4 turning points. It may have less, again, that all depends on the local behavior, what happens near and at the origin here. Okay. All right, so the last thing to cover here is this idea, and I kind of hinted at that at the previous example, right? This idea, local versus global extrema. Extreme I use as a term to refer to either maximum or minimum, right? Extreme values. Okay, now, as we saw with our cubic function, and really any odd degreed function has the same general form here. Right? Now, notice here that since this does go up to infinity, there's no global max, right? There's no value that I could say, all right, this is the largest value this function can attain, because it attains values that keep increasing, increasing, increasing. And the same for the decreasing, right? It decreases, 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 so there's no lowest value that the function attains. Right? But there are these kind of special kind of values here, here, and here, right? Where again, if we construct some kind of neighborhood near those values, it is in this case the lowest value, call that x1, and here, again, near it, it is the highest value, right? This value of nearby being the lowest or the highest, this one we would call a local max, excuse me, a local min, right? Where it's not the minimum of the function, right? Because we see there are smaller values, again, those values that are below this value here, but they don't occur near here, right? So local min at x1, right? The value of that min is f of x1, right? That would be that here, right? F of x1, right? And the same thing here, right? This is a what we call a local max. Okay, where the values near it are smaller than this f of x2, right? The max occurs at x sub 2, and it has the actual max, that is the output of the function, right? That max value is f of x2. It occurs at the input, x sub 2. Okay, all right, now, in general, right, odd degree polynomials don't have a global maximum because of the end behavior. But our even powered ones, they actually do have global maximum, right? That really depends on whether it has a positive coefficient or a negative coefficient, whether I have a global max or min. Right, so let's just take a look at the case where we have some kind of a even power, and the coefficient is some positive number. All right, so we know that here looks something like this. All right, so just kind of by looking at this, I know the degree is the polynomial is even, right, because these are both headed in the same direction for the end behavior. All right, so I know that. And it's 1, 2, 3, 4. All right, so possibly of degree 4. Okay. All right, and I think here, just based off of the way that these look here, this pretty much is a degree 4, and we have 1, 2, 3 turning points, so that matches up here. All right, now, previously we've identified local extrema, right? Just looking at the graph, this is a local min, local max, local min. All right. But in this particular value, I've actually have, right, a global min, right? Because if we look at it, if I draw kind of a straight dotted line here, there are no values of the function that drop below that line. All right, so that's what distinguishes a local min from a global min. There are no other values. This is the lowest the function gets. Right? Notice that didn't occur in our previous example in either case, right? The local max, there were values that were higher than that. The local min, there were values that were lower than that. But here, right, there are no values below this. So this is actually not just a local min, but it is a global minimum. Now there are no maximums, or excuse me, there are no global max because the values increase in both x heading towards positive infinity and negative infinity. The values of the function go towards infinity. Now if the coefficient was negative, all that would be flipped, right? We would have a global max and no global min. Okay? All right.